In this video, we will continue discussing the various techniques of integration by concentrating on rationalizing substitutions, which we will see in a few slides includes things that are also called trigonometric substitutions. So to begin with our rationalizing substitutions, the observation we want to make is that when you have radicals, square roots, cube roots, etc. inside an integral, they typically lead to difficult integrals for us to evaluate. And what we would like to do is somehow rationalize the integrand, which essentially means get rid of those square roots that are present, or cube roots. And one way we can do that is if you have an nth root of a linear term, by setting u equal to that nth root, what you can do is eliminate the radical. And before getting into maybe a more difficult example, I wanted to start off with something that was hopefully nice and simple. The integral that we're given here, e to the square root of x. This is not something that we can handle using our previous methods. There's no obvious algebraic simplification, substitution, integration by parts doesn't apply, and it's also not a trigonometric integral. But if we take the advice that we have above, we have a square root of x, we should be able to rationalize this by setting u equal to the square root of x. And to convert our integral solely in terms of u, I'm going to express this slightly differently. I'm going to write this as x equals u squared, so that dx is equal to 2u du. So it's a bit different than what we've done in the past, but notice the square root of x becomes u, and the dx we can rewrite as 2u du. So using this substitution, we have a 2 that pulls out front, and our remaining integral would be u e to the u du. And I'm not going to evaluate this integral. I'm going to leave it to you, but note when it's u e to the u, you can solve this very efficiently using integration by parts. So hopefully this illustrates how we can apply a rationalized substitution in maybe a more ideal case. Let's look at a slightly more involved example. So here we are asked to evaluate the integral of x times the cube root of x minus 4. So very similar to our previous example, we would like to apply one of these rationalizing substitutions. So in order to do so, what we need to do is set u equal to this cube root term inside our integral. So cube root of x minus 4 is u. Now to get the integral solely in terms of u, I find that it's often easiest to go ahead and work backwards here and rewrite x in terms of u. So if you cube both sides and add 4, you find that x is equal to u cubed plus 4, which implies that dx is 3u squared du. So looking now back to our integral, we see that the dx can become 3u squared du, and that this remaining x term can simply be written as a u cubed plus 4. And now we can take our integral, which started off solely in terms of x, and we can rewrite it solely in terms of u. So that x becomes u cubed plus 4, and then the leftover terms are u times 3u squared. 3 is a constant which pulls out front. U times u squared is u cubed. And now that we've made this rationalizing substitution, the resulting integral is much more reasonable for us to evaluate. We can simply take this u cubed, distribute it through, and then very efficiently anti-differentiate. So the 3 is hanging around out front. We'll have u to the 6 plus 4u cubed du. We anti-differentiate each term individually, so the 3 is going to hang around out front. We'll have 1/7 u to the 7th plus 4 over 4 u to the 4th plus c. And now we'll go ahead and take the 3 and distribute it through, and we will replace each u with the cube root of x minus 4. And recall that the cube root is really raising to the 1/3 power. So we have 3/7, and we have x minus 4 cube root raised to the 7th power. So 7/3 plus 3 times x minus 4 to the 4/3 plus c. Let me now make a second observation. So for this integral, we actually did not have to make a rationalizing substitution. It was just a really nice illustration of how we can use that method. Hopefully what you were thinking as we solved that was, can I just use a substitution? And the answer is absolutely. Going back to some examples we've seen previously, it would also make sense to say u is equal to x minus 4, so that du is equal to dx, and x is equal to u plus 4. So putting this integral once again solely in terms of u, we would have x is u plus 4, and then we would have the cube root of u, so u to the 1/3. And at this point, if you take the u to the 1/3 and you distribute it through, you get a very reasonable integral that you can evaluate. So I'm going to put a ... here indicating that I'm leaving the evaluation to you, but it's just illustrating that really we have two different methods we can apply to solve this same integral. Now, not all integrals that we'll see involving square roots would necessarily be of the given form. Another class involving square roots would have things like, say, the square root of a squared minus x squared, a squared plus x squared, or x squared minus a squared. And corresponding to seeing one of those expressions in your integrand, it turns out there's a corresponding what we would call trigonometric substitution, and then a necessary identity we would use to simplify. And the best way I think to explain how this works is to just illustrate with a few examples. So let's go ahead and do so. Let's evaluate the integral of the square root of 4 minus x squared. And let me just note before diving into this, none of our previous techniques apply. There's no obvious substitution, algebraic manipulation, integration by parts does not apply, and this is certainly not a trigonometric integral, at least not yet. So what we're going to do is try one of the substitutions from the previous slide. This 4 minus x squared. Another way to write that would be 2 squared minus x squared. So that is going to indicate that we try the trigonometric substitution, x equals 2 sine theta. And what we now need to do, much like our previous example, is to go from all x's to all thetas. So dx would be equal to 2 cosine theta d theta. So taking this integral purely in terms of x's and rewriting it in terms of thetas, we have the integral of the square root of 4 minus x squared. So if we square 2 sine of theta, that's our x, this will become 4 sine squared, and the dx is 2 cosine theta d theta. So we've made the desired substitution, 2 sine theta, based upon this expression 4 minus x squared that appears in our integrand. Once we have done so, there's a corresponding trig identity that we want to use. We know that 1 minus sine squared is cosine squared, so 4 minus 4 cosine squared is really 4 cosine squared. And the square root of 4 cosine squared is 2 cosine theta. So 2 times 2 is 4, and cosine times cosine is cosine squared. So we end up with 4 times the integral of cosine squared. And one of the reasons we call this a trigonometric substitution, besides the fact that it's in terms of a trig function, is that the integral becomes one of the trigonometric integrals that we have previously discussed. So kind of just to recap, based upon the 4 minus x squared, we make the substitution x equals 2 sine theta. We plug that in, we simplify with a corresponding Pythagorean identity, and it turns the integral into a familiar trigonometric integral. So to evaluate the integral of cosine squared, we rewrite it with that half angle formula for cosine squared. So that would be 1/2 1 plus cosine of 2 theta. So anti-differentiating term by term, we would have theta plus 1/2 sine of 2 theta. And what we need to do now is take our solution here, which only involves thetas, and rewrite it somehow in terms of x's. So to do so, we're always going to use a similar technique. We started off with x equals 2 sine theta. So x over 2 is equal to sine of theta. To get everything back in terms of x, what we can do is just draw the corresponding right triangle. So x over 2 is sine of theta. So x 2. And when we use this technique, the x and the 2 in this case allow us to label two sides of the right triangle. The remaining side that needs to be labeled, we can think of labeling it by the Pythagorean theorem. This would be 4 minus x squared underneath the square root. And note that how we've labeled this side, the square root of 4 minus x squared, is exactly what we see in this original integral. So it's kind of just a visual double check. Now, in terms of getting back in terms of x, we can go ahead and just immediately write down what theta is by thinking about using inverse trig functions. Theta would be inverse sine of x over 2. So arc sine of x over 2. But for the 1/2 sine 2 theta, we need to make another observation here to the side. So 1/2 sine 2 theta, we can use the double angle formula for sine. So sine 2 theta is really 2 sine theta cosine theta. So the 1/2 times 2 goes away. So 1/2 of sine 2 theta is really sine theta times cosine theta. So sine theta is x over 2 multiplied by cosine of theta. Cosine is adjacent over hypotenuse. So cosine of theta is the square root of 4 minus x squared over 2. So in terms of doing a trigonometric substitution, you can very clearly see in this example, it's not always going to be a quick, efficient process, but procedurally, it will work out in a similar fashion. Based upon the expression we see, we make a trig substitution, we get a resulting trigonometric integral. We evaluate the trigonometric integral using our previous techniques. If it's an indefinite integral, as we have in this case, we draw a corresponding right triangle to rewrite in terms of that original variable x. And we'll see some more examples in a future video. Let's finish with just a few key observations. So a trig substitution takes an integral that involves certain types of expression and it converts it into a trigonometric integral we can solve using our previous techniques. If it's an indefinite integral, our last step is going to be this resubstitution, which requires us to draw a corresponding right triangle. If it's a definite integral, as we will see, you must change your limits of integration. And additionally, occasionally before applying the trig substitution, you may need to do some algebraic manipulation or even a substitution to get it into that desired form.